So the last part I will use to tell you a little bit about the flood risk reduction at the Galveston-Houston Bay area. For a couple of years now we are working on this problem, so to speak. We are working with the Delft University of Technology, Royal Haskoning DHV, and recently with Rijkswaterstaat. Mark Rolhaven also joined our team. We have a core team of Bas Jonkman, which is a professor in Delft. You may be aware of him. And Matthijs van Ledde, who is also speaking on Wednesday here for you guys. So pay attention to him. He's a very bright guy. And then all people from those companies. And on Texas side, we have the A&M University. Professor Bill Merrill is the big initiator of this whole plan. And he's working with Sam Brody and Len Waterworth. And recently they joined forces with the Rice University. And now they have a real strong combination of enthusiastic people who are really going for a barrier over there. Because it's completely different in the US. If you experience a risk to you, then the government doesn't jump in automatically. We are very used to the Netherlands, in which the government comes up with the plans for a storm surge barrier, like the Maasland barrier, like the storm surge barrier in the Eastern Scheldt. But in the US, it's a different way of politics, and you have to come up with your own ideas and come up with your own money even. About half of the budget should come from private parties, and then the US government by the core, the core of engineers is willing to pay not more than half of the budget, normally. So there's a completely different situation. Okay, so to tell you something about the region we are talking about, it's, as you well know, it's Texas, where George Bush comes from. So it's the cowboy country. It's in the south. It's in the southern part of the U.S. It's also situated in the Gulf of Mexico, of course, which is a very severe, very dangerous area if it comes to hurricanes. And here we zoom in, and this is Galveston Island, and this is called the Galveston Bay, and that's maybe not that interesting to most of the people in the world, but here is Houston with the Port of Houston and the petrochemical industry. And it's a real big city, and it's growing rapidly, very rapidly. It's home to more than 2 million people, and it may double by 2050. It's the 4th biggest city of the USA already, and still growing. It's the strongest growing area even. And if you look a little bigger around Houston, you can find already 6 million people living there. So it's the 5th most populated metropolitan area even. Now, it holds a lot of valuable ecosystems like oysters and a lot of green stuff. Supports the largest petrochemical complex in the US, and that's maybe even the biggest reason for defending it, because if a real hurricane should hit Houston, then we have a problem. Not only Houston, we have a problem. So the Port of Houston is 2nd in the US in total tonnage. So it's biggest over there. And the strange thing is, it is not protected at all against hurricanes. And every 15 years, a real hurricane hits this area. They are channeled up at the bay, and they are blown towards the petrochemical industry. The way Houston is built is that it's very difficult to evacuate the people, and you will probably have, well, 10 or maybe even 10,000 of death if it really hits. And of course, a lot of ecosystems and infrastructure will get lost. It's also an area in which a lot of, well, vulnerable people live, so to speak, in the lower class There are also a lot of rich people, but a lot of vulnerable people live there. So just like in New Orleans, the problem is not the direct kills, but the problems that are coming after Katrina. Years and years, this city never returned to its full glory as it was before Katrina, because a lot of people run, they move, and they never come back. Here you can see all the hurricanes that hit this area between 1851 and 2005, and the colors are difficult to see, but there are category 5, 4, and 3 hurricanes. So the category 3 hurricanes are much more often, of course, and the category 5's Rita, maybe you can remember that one in 2005, was a big one. Again, a female name, Edith and Audrey and Alicia. Here we have the return periods for all the hurricanes in this area. So here we have Alabama, Mississippi, Louisiana, and here's Texas. And this is the area 4, in which you can see that every 3 years a tropical storm or a hurricane hits. Every 8 years we have a hurricane at least, and every 26 years we have a real serious hurricane of category 3 or higher. So this is, well, pretty amazing. If you look at all these numbers, then the numbers for Texas are almost the lowest, which means that they are being hit most of the times. And the protection is, as I said before, about 0. In 2008, Ike passed by, and Ike is a male name in this case, and it really struck, and it was also very difficult to tell where Ike would struck in the end. As you can see here, these were the forecasts. So on Tuesday at 4 AM they thought Ike would go like this. On Wednesday they changed its course, and they all have systems in the US that forecast the path of a hurricane, because it's very important if you want to evacuate your people. And they changed it on Thursday morning to the green line here, 4 AM, and they changed it already on Thursday, 4 PM, more to the east. And in the end, luckily, very luckily, it ended up here. So this is the path Ike took. And Ike was a very big hurricane. As you can see over here, this was the satellite picture taken when just before Ike hit the Houston area. So on September 13, Ike did really pass, killing approximately 48 people in that area. It had already made a lot of casualties in the Caribbean and in other areas, so about a little less than 200 casualties in total, but it also cost more than $30 billion. And for those who don't know, that's a milliard. Here's some pictures taken just after Ike. So this is on the Galveston Island, on Bolivar. You can see a cemetery. This was very, very hard hit. This area. These islands were hit the worst, and it was even not from the front, but they were attacked from the back actually. So Ike did have what they call a front runner. So just before everyone was aware of Ike coming, a lot of water was already going into the bay, and then Ike passed by, and Ike took up the water and blew it from the back over the islands, and that's what happened over there. Well, you can see the house from the only engineer over there probably. The rest was devastated. Little boats everywhere, and this was the city center. So, serious business. But like I said, we were lucky that it hit Houston on the east side, because had it hit farther west, then if you still remember the question about where to go to, the dirty side of the hurricane is always on the right upper side, on the east side. So if Ike would have hit a little more to the west, then the center of all the damage would have been right on the spot, right on Galveston and right on Houston. So we would have thousands of more lives lost, probably billions more in damage. And the Perryman report even talks about $73 billion losses if that would have happened. If a Katrina-like hurricane would hit, so that's a Category 5 hurricane. And Katrina was the hurricane that devastated New Orleans. And Bill Merrill, Professor Bill Merrill, always talks about we dodged a bullet, even if it was bad. So they came up with an idea. This is the idea of Bill Merrill, and it's called the Ike Dike, which is an interesting name because in the Netherlands we know the Eikdijk, which is a dike or a levee with all kind of measurement devices in it, so we can measure how the dike responds to wave loads and things like that. But this is something completely different. So if you hear of the Eikdijk, it's not the same as the Ike Dike in Houston. The Ike Dike is an idea of Bill Merrill in which he wants to shorten the coastline. He is very much inspired by the Delta works in the Netherlands. He visits the Netherlands at least once every year, and he can't stop talking about how beautiful the Eastern Scheldt and the Maasland barriers are, and so that's great to see. And in every drawing he makes, a Maasland barrier is pictured, and so we really had to convince him that it's not the best solution at all over there. But he wants to shorten the coastline and create a coastal spine. And there is already a seawall, the Galveston seawall it's called. It's a relatively small piece of wall, actually, and that has to protect all of this. A little ambitious. 17-ton fixed barrier. The positive thing is it did hold last time. After it held when Ike passed by, and the last time another hurricane came by, and the Galveston seawall is strong enough. It has done its job preventing catastrophic Gulf overflow. But the back surge, what I was talking about, is of course not helping here. Now they want to extend this seawall, and they are very enthusiastic about this built by nature, building with nature concepts we are using in the Netherlands. So we kind of hide a barrier in a dune. We put a lot of sand on it, and it looks like a natural barrier, but in fact it's a very civil structure underneath it. This Bill Merrill and his colleagues are really enthusiastic about that concept, and they want us to build something like that over there too. But there's one big issue if you want to close. Here it's easy, yeah? You just extend this wall and you make levees and dikes, but here you have a gap of about 3 kilometers, which is a very important gap, because if you can see on the color that here we have the channel for all the ships to the Houston port. So we cannot close off this gap, because that will be an economic disaster. So it should be something like a movable barrier, of course, which is open under normal circumstances and will close when the storm is hitting. So here we're talking about, if we take another cross-section, then this is what it looks like. Here we have the 3 kilometers with, of course, the navigational section. This is what they dredge every time, because to keep, of course, the depth for the ships, for the major ships going over there. And then we have a lot of water that is needed not only for the navigational activity, but it's also very important for the ecological systems, because we have to have in and outlet of the water, so to keep the tidal working going on there. Otherwise it will be dead water behind the barrier. So we need to keep this part open too. That's one of the challenges. And we have an important challenge that we have to come up with a solution that can resist the negative head. And a negative head is when the water inside the bay is higher than the water outside of the bay. And if that happens with the Maasland barrier, for instance, then our Maasland barrier will be drifting somewhere in England, if that happens in the Netherlands. So the Maasland barrier is designed in such a way that when the water in the new waterway will be higher than on the North Sea, then the Maasland barrier will open up a little bit, leave the water out of it, and then it can close again. Not many people know that, but that's the system behind the Maasland barrier. Otherwise, this whole mechanism in which the Maasland barrier is moved will be lifted up and will just float away. So you can also come up with a solution that prevents that, but it's going to be a little forced. So we have to come up with a solution that's something else than the Maasland barrier, which was very disappointing for Professor Bill Merrill. So we made a lot of investigations and studies. Many students worked on this project at the Delft University of Technology. So we did some measurements to the bathymetry. The hydraulics were mapped by Maarten Ruijs, as you can see here. So we wanted to know how much can you close and how much can you leave open. Or do you need to leave open just to keep the ecological system alive? And it shows that it's about 60-40%. So you have to leave at least 40% open for tidal flow, otherwise you will ruin the system. And another student, Casper Stoeten, who is now working for Arcadis, built a probabilistic search model, so we could calculate the wave heights related to the probability of occurrence, because you can, a lot of people in the US are very used to design a barrier and they take the last real severe storm and they say, well, the water can go up to 25 feet and so we have to make a barrier like this, which is of course one way to do that, but we are very used to work with probabilistic modeling in the Netherlands, and all of our dikes, you are probably very much aware of that, are designed based on probabilistic heights. So we just make probabilistic search models and we calculate the height of each of the dikes in the Netherlands. It's even in our Water Act that we have to do it like that. And we wanted to use the same strategy in the US, and they really have to adopt to that, because it's new to them. It's very new to them if we say we wanna protect you with once every 1250 years or something. Now, this is one of the concepts we came up with using a couple of workshops with all the professors and experts we could find in the Netherlands. We sat together and we just invented some interesting ideas. This is something Professor Hennis de Ridder came up with, which we call the hinge gate. It could close automatically on the tidal flow working. But later on we realized that it's going to be very heavy and it could alter when the waves come in a certain pattern. So then it would close, open, so that's not something you would like to have. So we changed that to caissons, like we see over here. And that's for the environmental part. So that's something like an Eastern Scheldt solution. We want to keep it open under normal circumstances with a lot of gates in it. You can see the gates. We should close them when the storm is coming. And then the interesting part, of course, is the navigational part. We have to come up with a solution, and the cheapest solution was a barge gate, which is kind of a big ship or a big shoebox, whatever, laying at the side, and whenever the storm comes, you just close the gate. It's that easy. Well, it's not that easy, unfortunately. If we looked better at the environmental section, we found out that the soil over there is, well, very soft, and we have to go very deep with our piles and our foundations to give this enough stability. So the whole solution with caissons without piles is not working, probably, so we have to come up with another solution. So this is what Peter de Vries found out in his thesis. So still work in progress. For the movable barrier, luckily we came up with a lot of piles, 40 meters deep, and we did some structural analysis because it's a very long shoebox, and there are stories, and it's really true, of Chinese vessels that are too big and they simply broke in the middle. If you Google on that, you can find ships that just cracked in the middle because they were too long and not calculated well enough to take up all the forces of the ocean, because you have waves and suddenly a wave can do like this or can do like this and then it just breaks. But you have to be aware of that phenomenon for this barrier too. So we did a lot of structural analysis at IV Infra just to came up with how much distance can we keep from the ground in order to, well, to make a solution for the under pressure that will exist over here and still keep this scour protection laying over there. This is a very difficult calculation. We have to make special devices on the side just to keep it floating and make it stable enough, so it's going to be like a kind of catamaran type. And what we create over here is in which what we call the woelbak in the Netherlands. I don't know the English word for that, but and so a lot of forces will be removed under the barrier then, so it will lose a lot of its energy. That's what I'm trying to say. And then the forces will be much less for the under pressure. Well, we did some study about how high should it be. We can build a barrier 10 meters high, but Katarina Rippi, one of our students, also made some calculations, and it's interesting that you can see the total inflow in meters of the Galveston Bay against the height of the barrier, as you can see here, amongst the horizontal axis. And this is the inflow through the barrier, and this is the wind setup. So there will be a lot of high water because of the wind blowing on the Galveston Bay itself. So whether you have a barrier or not, you will have those setups anyway. So what you can see here is that even if you make a higher barrier all the time, the total amount of water coming in is about the same. So the optimum is about here, which is it's a little more than 3.5 meters high. It should not be higher than that. It's a waste of money. That was also convincing stuff for the Americans. And then a very interesting thing was, how do we put the barrier in place? Because when a hurricane comes towards you and you have to move a barrier with a couple of ropes and cables, you should be on time, otherwise the sea will be very rough and it will be very difficult to make a decent closure. So we also made a lot of calculations using ropes, and the design is in such a way that it can actually close by itself using the currents in the right direction. So we only have to loosen it on the side, and then the current will take it and it will just close it. But of course, if you do that, then it will hit the end post with a lot of speed and a lot of damage. So you have to control its movements. So we are thinking of using a lot of cables and trying to do that like this in a gentle way. But of course, then you have to do something with your cables when it's not over there. You can put them on the ground, but you also want to dredge here. So it's a little difficult. And we take a lot of looks at the stability, and it's very difficult to keep it balanced during its movement, because it will go every way on the waves. So we need some side skirts, we need some catamaran types, but we think it's possible, but it's going to be difficult. Well, I told you about that one. Yeah, I told you before about the negative head. It can also, of course, exist in this type of barrier. So we should have a solution that we open up the barrier a little bit just to leave the water out, and then we can close the barrier again. Otherwise, the forces will be very high. And it's only pushing against the wall on that side, but not on the other side. So if the water is going here, then it can also open up by itself. So that's not a good idea. Of course, we can lock it with all kind of solutions, but I'm very much specialized in reliability engineering and all things like automatic locks and things like that. You don't want to have that. Now, luckily there are more solutions, because this Rice University also has a master plan in which they have some local protection measures everywhere. So they have small barriers at the port, and they have some extra dikes and protection levels here. They are still very much in debate about what kind of solution should be the best here. The good thing is that they used to have two camps, two people standing against each other, two organizations with their own ideas. So we have A&M University, who wanted this barrier and this coastal spine, and we had Speed Center from Rice University, who had all these local measures. But recently, about half a year ago or a year ago, they joined forces, and now they come up with a master plan. So that's a very good thing, because otherwise you won't get any money at all, because the politicians would say, just keep up your mind and come up with a good idea, and then we put money in it. So we are now working on, of course, further designing this barrier, because it's very rough so far. We are working on the land barrier. So that should be an interesting one, looking naturally, but still defending the Galveston Island and the Bolivar Roads. Royal Haskoning is working on that one. Wetlands, local levies. Of course, we are very much with the cost estimates, because half of the money should come from private people. So they're all millionaires, but still they're a millionaire for a reason. So they really want to know where you spend your money. And the next job for us, and that's something we will do with Mark Walraaf from Rijkswaterstaat, is O&M optimization. So they are really interested in the lessons learned from the Netherlands, from the Maasland barriers, stormsurge barriers in Eastern Scheldt, Ramspool, Haringvlietsluizen. What are the tips and tricks for us if we design a new barrier to optimize our operations and maintenance costs? So don't put any parts underwater. We just saw it in Venice. You're all creating a lot of problems, so if you can avoid it, please do. Hydraulics, still interesting, because the models are not in line with each other over there, so we have to make one good model for hydraulics. And we have to do the real risk analysis over there, because we never really calculated the amount of expected people killed, the damage in cost, etc. And then we can optimize the height of the barrier, of course. Other concepts are also still taking into account, like the inflatable barrier we have in Ramspool in the northern part of the Netherlands. Well, the good thing is, money is coming. So here, it's a bad picture, but $3.6 million to study flooding for the university. So this is for A&M University and for Rice University. And the good thing is that the Army Corps of Engineers finally got their approval to study the coastal barrier study. This took at least 3 or 5 years or something for them. So the Army Corps of Engineers is the Dutch Rijkswaterstaat, is the American Rijkswaterstaat. So they are now studying the barrier, and then they will decide what the best solution is. But it's still a lot of things to do over there. It's still very interesting work for the Netherlands to support the Americans over there and jointly build a good defense system for Houston. So far, my presentation. Any questions? No? Thank you for it. One here. Ja, hiervoor. We doen het ook helemaal professioneel.
Yeah, I have a question. You said that during a hurricane there was also on the back of the hurricane an attack on Galveston Island.
Yeah.
I didn't see anything about protection that island on the backside.
No, the whole idea is that what happened during Ike was that Ike had this front runner which came about a day before the real hurricane struck, and a lot of water was already pushed inside the bay. Then Ike passed, and Ike just rotated counterclockwise, and then it took up a lot of water from the bay and just threw it back to the islands. And this idea now is even to keep the front runner already outside, so don't let the water in at all. So you have to be on time. Otherwise, if you close off too late, even with this concept, you still have the same problem. Yeah.
And another question is, you said also that due to wave setup, yeah, the coast of Houston itself the water level will increase.
Yeah.
What are you doing on coast protection on that part of Houston?
Just levees, dikes. There should be, or walls, or like in New Orleans, they are very much a fan of these T-walls, the Americans. So you see them a lot in New Orleans, and we have all kind of solutions like natural dune-like kind of warriors, and you can use breakwaters, of course. This is what we are, just keep the energy out of the waves. That's what we should do here. But now there's nothing, almost nothing, because I say almost nothing because all the petrochemical industries put on their own defense systems around their chemical plants, of course. They're not that idiot. Yeah?
Thank you very much. And we have some present for you.
Thank you. Thank you. Thank you.